Awesome. I love all these answers. Let's make sure we have our notes open and ready to go. Today we're going to be talking about work and energy in a physics context. So it's important for us to start brainstorming about what do we already know about those words. Here are the links. Feel free to start raising your hands once you have your notes open and ready to go. Remember, you can do your notes at any time during the trimester and still get notes credit, but if you also want attendance, you do need to be doing it during class. So make sure that you are doing your notes during class and that you do actually pass them. You should always pass them. We always give you enough answers to pass, so you should do well on these. Let's go over some announcements while you're still opening up those notes.
Please not share any personal information during class, guys. Your participation is required, and that these class sessions are recorded for learning purposes. All right, we're at the start of a brand new week and a brand new unit. Let's see what we're learning about today. All right, so we're starting a new unit called Unit 3, Energy and Work. We're going to learn about what those two things are and how they're different. We're going to be learning about mechanics, machines, and energy. Okay, I thought skipped a slide. Okay, there we are. Yeah, so today we will be able to define energy and work and describe various types of energy. And then hopefully by the end, we should all be doing well with our notes. So let's go ahead and open those right now.
All right, friends, we already have a lot of people with their hands raised, so thank you, Lena, Mallory, Carlos, Angelina, Noah, Shayna, Benjamin, Jonathan, Alicia, and Jaime on top of it. I love it. Let's get some more hands raised. Thank you, Itati. I will give you 20 more seconds. Links are in the chat. If you're having issues, please just communicate as always. What I want to know in the chat, another brainstorm, just thinking again through how we think about energy. How do you try to gain energy when you're tired? So, for example, I got 4 hours of sleep last night, so I need a little bit of energy. How would you recommend I get more energy? Go ahead and tell me in the chat. Awesome. I see Callie. Yeah, sleep, caffeine. That could come in the form of coffee. Eating, yeah, sometimes just eating some food, especially sugary food, can help give you a burst of energy. An energy bar, absolutely. Other things that you can think of that would help give me energy when I'm really tired right now since I didn't get a lot of sleep last night. Tell me in the chat. Yeah, drinking water. Sometimes if you're dehydrated, that can make you feel more tired. Absolutely. Anything else you can think of? I know, for example, that sometimes it's easier for me to stay awake if I do a little bit of exercise, right? A lot of exercise will make me more tired, but I remember when I was in college, for example, and I needed to stay awake for an all-nighter, I would do a lap around my dorm room, my dormitory, and that would help me to stay awake. If I ran around a lap, I would suddenly have a little bit more energy. Excellent. So we kind of have an idea of what energy is, right? We know that somehow it's making things happen in our world. But let's go ahead and go over the definitions that we will be using in our physics course. Here we go.
Learn how to define energy and work. So energy is the ability to do work. So this can come in many forms, all of which we will discuss in the future, including chemical, electrical, heat, light, mechanical, sound. So for example, like when we eat something, the food, right, goes into our stomachs and is processed by our body. And so that's kind of like chemical energy. When you turn on a light switch, all right, that's electrical energy. Um, when we like let's say when we turn on our stove to heat a pot of boiling water, that would be heat energy. Like let's think of solar panels, so that would be light energy being converted to electrical energy, right? So all of which can be converted into each other, and remember from our laws of uh, it wasn't Newton's laws. It was some of the laws that we learned, I think, previously, where remember we learned energy cannot be created or destroyed, all right? And then work is the result of forces acting upon an object causing it to move. All right. So then from that, we have this equation where we can relate work to force, which we already know, and distance. So if like let's say we're pushing a box that weighs 10 newtons and we push it for a distance of 10 meters, that would give us some amount of work. All right, so let's move on from there. Actually, you know what? Uh, yeah, give me an expression using this poll. How do we feel about this so far? One neutral, couple neutrals. Again, we're going to be going more into this. This is just a general brief overview.
All right, so we're going to be going over these different types of energy, and later on in our unit, we'll talk a little bit more about work. But again, energy is how we actually do stuff in our world, how things change. All right, so chemical energy is a type of energy that gets stored in chemical compounds and then can be released when those compounds undergo chemical reactions. So there are two types of chemical reactions. There are endothermic reactions, which absorb energy from what's around them. So tell me in the chat, endo, does that sound more like the word enter or exit? Tell me in the chat, does endo sound more like enter or exit? Yeah, it sounds more like enter, right? So again, this means that energy is entering the chemical reaction. Smiley faces emojis in the chat if that makes sense. You'll need to know this later on, so start committing this to memory. Excellent. Now, exothermic reactions, on the other hand, will release energy to the surroundings. And what does the prefix exo mean? What does the prefix exo mean or sound like? If endo means enters, exo means what? Close. Think about a word that also starts with ex. So if endo means enter, en, endo, enter, exo, ex means what? Yeah, this means that the energy actually is released or exits. It goes out of the reaction. And just so you know, this ending part, thermic, means heat. So specifically, when we're talking about the type of energy that's going in or out of chemical reactions, it's heat. All right. So here are some examples, all right, things that have chemicals that are then used in order to power things. So for example, batteries and flashlights, all right, batteries are have chemicals inside of them. That's why when your batteries go bad after a while, you can see all that crusty stuff that develops on the batteries. That's because the chemicals inside of them are being released and are forming that crustiness, right, which is gross. But batteries in a flashlight are chemically based, chemical batteries. Yeah, exactly, Jonathan. Where another example would be burning gasoline, gasoline within a car. Gasoline is a chemical, and when you burn it, that is what makes your car move. So that's a type of energy that your car is moving. Same thing with your body, all right? You eat food. Food is made of chemicals, right? Don't listen to people who say, oh, I don't like chemicals in my food. All food is chemicals. And so chemicals in your food are then used and burned in your body to give you energy. Go ahead and give me a green check, orange X if that makes sense. What chemical energy is. All right, an example here would be a butane lighter. So I have a butane lighter right here. And what you'll notice is that it's a little bit hard to see, but butane lighters have a liquid inside of them. And that liquid is called butane. So butane is a type of chemical that reacts with oxygen. And when it reacts with oxygen with a spark, it forms carbon dioxide, water, and heat. And that heat is in the form of what? That heat is in the form of a flame, right? So this is a chemical reaction. We can actually know that chemical reaction's happening because it's forming a flame as well as it's forming some other chemicals. All right, so let's go ahead and talk a little bit. I know scientists are geniuses, right? Let's go ahead and talk a little bit about electrical energy.
Electrical energy. So electrical energy is movement of electrical charges. It can be used to power light bulbs and other electrical devices, natural or generated from other energy sources. So, uh, generated could be from oil, coal, or nuclear power plants. So, every time you see an oil plant that's burning the oil and releasing smoke, the soot and the ash, that is a byproduct from them burning that oil or that coal to generate power. We also have geothermal plants that generate heat, hydroelectrical plants from water, and wind farms and solar radiation. So all these are different methods of generating electrical energy. So this is just another example of how electrical energy, right, it can be used to convert from one form of energy to another. So for number two, let's write the word charges for number two. And let's raise our hands when we are done with that. I will set my timer.
All right, everyone. So I want to go ahead and show you an example of how electrical energy can be formed in many different ways. So let me go ahead and share this with you up on the whiteboard. And I will also send the link to you because I know that these demos are always lots of fun to play with on your own as well. So let me go ahead and send this link to you in the chat. And we're going to go ahead and we are going to go to the systems area. So we're going to look at these systems. Okay, so this is pretty interesting. There are many different ways that we can form energy. We're going to look at specifically talking about electrical energy, which is like, for example, if we light a light bulb, right? So let's go ahead and take a look. So we could have someone, for example, use biking. All right, and biking is where they're taking chemical energy from food and they're changing it into motion, which is a type of mechanical energy that we'll talk about in a moment. And that motion can be used to create electrical energy through an electrical generator. So you can see these blue. Oh, gotta feed our person. You can see these blue squares, which are electrical energy, and then they actually create light energy as well as heat, thermal energy. So you can see that changing into both red and yellow boxes here as it creates both thermal and light energy. Yeah, so dams work on similar ideas of this idea that we can change energy. All right, smiley faces, emojis in the chat box if that makes sense. You can also use running water. So this is an example of a dam. So running water from a dam will create mechanical energy or motion. We'll talk about that again later. Again, you can use that with a generator and that'll create your electricity that can then be used to make different things happen. You could also make this move a fan, for example. A fan would actually be turning it back into motion or mechanical energy. Excellent. All right, let's go ahead and take a look then. I could also use the sun, right? And if I had a solar panel, the sun will actually give us light energy, which can then be turned into electrical energy to then be turned back into light energy, as well as heat energy. Again, light bulbs also release some heat energy. And, right, we can see here that we can use thermal energy. Right, this would be like from the earth, geothermal energy, which represented by the hot air coming from this steam. That can be used to turn a turbine as well, and again to create electricity and our light. Go ahead and give me a green check or an orange X if that's beginning to make more sense about where we see all these different types of energy and the fact that they can change from one type to another. So we can change from one type to another. I'm showing you how we can create electricity, different ways we create electricity. Excellent. All right, let's go ahead and jump back over to our PowerPoint and continue talking about some other types of energy.
Or thermal energy, as it'll sometimes be referred to, is the activity of a substance's particles. So as we know with particles and phases, when we heat something up, the particles that make up that substance or that matter start to move faster. So here we have cold air. The motion lines are very, very small, so they're moving slower. And hot air, when they're heated up, the particles are moving faster and more rapidly. So again, very hot molecules are moving very fast and collide often with a lot of energy. Very cold particles are moving slowly and colliding with less and are colliding less with little energy. So for number 3, go ahead and mark the word activity in your notes.
Then heat energy. So again, if you already had chemistry, this should look very familiar, but if not, we're going to go ahead and do a brief rundown of it just in case. All right, so let's go ahead and take a look at what goes on when we add heat. All right, so what you can see here is that I'm going to go ahead and add some particles here. So let me add some particles to this area. All right, and what we're going to go ahead and do is we are going to go ahead and take a look at what happens when we begin to add heat. All right, so what you can see is currently we're at 361 Kelvin, which is about 88 degrees Celsius. And as I add heat, what do you notice happening to the particles? Go ahead and tell me in the chat. What do you notice happening to the motion of the particles? We're getting up to thousands of kelvins now. Tell me in the chat. Cody, awesome. Yeah, they're moving faster and faster, right? They're getting crazy fast. And in fact, at some point, they'll get so fast that they're banging against the side of these containers and they're creating what's called pressure until it actually bursts through the tank. Right? So this is like, for example, if you have a propane tank outside and it gets too close to a fire source, it can actually cause an explosion. So again, the more that you add, right, the more that you add heat to a scenario, the faster and faster the particles will move. Go ahead and give me a smiley face or an emoji or a yes in the chat if that helps you to make a little bit more sense of what we were seeing on the previous slide. I know pictures are helpful, but sometimes seeing it in motion is also helpful. And let's talk a little bit about light energy. So light energy is comes from light. All right, so this one kind of self-explanatory on that, but light is specifically defined as a stream of photons. If you think about the word photon, you'll notice that it starts out with the 5 letters for photo, and so photographs, for example, need light. That's a good way to remember that photons are related to light. So what photons are, they are these tiny little packets of light. However, they do not actually have mass. So when we talk about matter and stuff in our universe, and we talk about things with mass and volume, things that are made up of atoms and so forth, all the physical substances in our world, light is actually not one of those. Light is not a physical substance, which kind of blows my mind every time I think about it, but light does not have mass and is not a physical substance. All right, go ahead and give me a green check, orange X if you understand that definition. Again, light is not a physical substance. It's made up of photons that don't have mass. Now, these photons can also move in a pattern of waves, all right, which is where we get this idea of light waves. And these light waves move at the speed of light, which is 299,792,458 meters per second, which is the fastest that anything can move. This is called the speed of light. Speed of light is as fast as anything can move that we have discovered so far in our universe, although science can always change later on. Now, light energy is not the same as heat or thermal energy. You can have light without having heat or thermal energy, but they do usually occur together, right? So usually if you think about a light bulb becomes hot as well as it gives off light, but they are different types of energy. So you can see some different examples of light energy. Light energy can actually come in different forms. So radio waves and microwaves are actually both forms of light energy. We use radio waves to communicate, microwaves, for example, to cook food. Infrared waves can be used in order to see in the dark. We can use infrared radiation. Visible light is the colors that you can see. So visible light is color. Ultraviolet light, which comes from the sun and can cause skin cancer over time. X-rays, which we can use to see inside the body, and gamma rays, which we can use for cancer purposes to try to eradicate cancer, but can actually also cause cancer during things like nuclear fallout. Okay, gotcha, Jonathan. All right, this is number 4. Go ahead and fill in the blank with the word photons. Make sure you spell it correctly. You have 20 seconds to get that done. I already see about 10 of you with it done. Everyone else, please raise your hands for number 4. Okay, so mechanical energy I mentioned a few times when we were taking a look at our demo earlier with the different types of energy changing. Mechanical energy is the energy of motion and position. So mechanical energy actually comes in 2 types. There's kinetic energy and there's potential energy. Remember that the word kinetic should always mean what? Tell me in the chat. We've seen this word before. What does the word kinetic mean? We've talked about kinetic energy, or we're talking about kinetic energy. We've talked about kinetic friction, for example. Tell me, what does the word kinetic mean? If you need a hint, there's a definition up on the board. What does the word kinetic mean? Yeah, kinetic means movement or motion, exactly. So when you think of kinetic energy, you should think of the energy of motion. So this is the energy that an object will have because it is specifically moving. Now, potential energy, on the other hand, is the potential for an object to begin moving. So this is before the object actually starts moving or it begins moving as fast as it possibly could. So potential energy is the energy that an object has stored, right? And that is because of its position or height above the ground. So for example, you can see right here at the top of this roller coaster, currently our rider has as much potential to fall as possible. Smiley faces, emojis in the chat if that makes sense. They're at the highest position. They have the most potential to fall here. So this is why this is called potential energy. So they have 100% potential energy. At the bottom of a hill, that's where they're moving the fastest. This is actually going to be related to your project. Your project will be related to designing a roller coaster, FYI. But at the bottom here, you can see that they're moving the absolute fastest that they can be moving. And so because of that, they have all kinetic energy. Kinetic meaning the energy of motion. They have no more potential energy because they can't fall any further. So they have no more potential energy. And everyone else, they have a little bit of both, right? So right here, they have some kinetic energy. They're moving a little bit faster, but not as fast as they could be, right? So they have like a medium speed. And they also have a medium height. So they have a little bit of kinetic energy and a little bit of potential energy, the potential to still fall a little bit further. Let's go ahead and take a look at this in action because again, I feel like it always makes more sense when we can actually see it in action. I'm going to go ahead and screen share this with you up on the board. Here is the skate park demo, so feel free to play around with that one on your own. So here we can see the skater, all right? And what we're going to go ahead and do is we are going to go ahead and imagine there's no friction, right? So we don't need to worry about thermal energy. So I'm going to go ahead and release the skater, okay? And what you will see here, so I'll put it in slow motion, is that their kinetic and potential energy is kind of changing back and forth. So at the bottom of the hill, for example, right? So at the bottom of the hill, they have no potential energy. They can't fall any further. And they have all kinetic energy because they're moving as fast as they can be moving, right? If I show you the speed, they're moving at 7.3 meters per second. Once they get to the top of the hill, though, you can see that now they have almost no, oops, sorry, let's try that again. All right, at the top of the hill, they have almost all potential energy because they're as high as they could possibly be, so they have the potential to fall the furthest, and almost no kinetic energy. You can see that they're getting really, really slow. Right, let's see if I can get it even slower. Yeah, so they're getting really slow here, almost no kinetic energy. In total, though, their energy is staying the same. You can see this yellow line here. In total, their energy is staying the same because of conservation of energy. Go ahead, give me a green check, orange X if that's beginning to make sense, if you feel comfortable with that. Again, kinetic energy, energy of motion, potential energy, energy of position, your potential to fall. And together, in total, they still add up to the same amount, no matter where the skater is on the hill. Okay, so one of the other types of energy we want to talk about is sound energy. Sound energy is due to vibrations. So this is one that you might not think about as often, but all the sound around you is a type of energy. The reason why is because sounds cause air molecules to vibrate. Those vibrations are then sent through the air until they reach your ears. So you can see right here a speakerphone emitting sound, sending that through the air until it hits your ear. Okay, and what happens is your ears have really interesting things going on in them. They literally have an eardrum that sound hits off of, and then you have a bunch of mechanisms in your ear as well as traveling to your brain that allows you to translate that into sound. So this is pretty fascinating that we can actually detect vibrations in the air, and that creates sound in our brains. Go ahead and give me a thumbs up, smiley face, emoji, or a yes in the chat if that's beginning to make sense. Super cool to think about. Let's go ahead and take a look at a video of this in action. Again, I want to prove to you that sound is in fact a form of energy. So let me share this with you up on the board. All right, I'll go ahead and replay that. Tell me in the chat, what are you observing? What do you see here? We have a fluid called a non-Newtonian fluid. It's just made of cornstarch and water, which helps to keep its shape when things are moving. So what do you notice as the speaker is vibrating? What do you notice happening? I see Cody in the chat. This is so trippy. Yeah, it looks like it's alive, right? So we can actually see that motion of the sound being transmitted to this fluid, which helps you to better visualize the fact that sound is a type of energy. Go ahead and give me a smiley emoji or a yes in the chat if that makes sense. Again, sound is a type of energy. Even though it might not seem as obvious as some of the others we might have talked about, it is definitely a type of energy. We just saw proof of that. This is the answer to number 5. Please fill in the blank with the word air, only the word air. Make sure you spell it correctly and raise your hands. So this last one you do need to do on your own. These are other things that we define during class. Please don't put answers in the main chat, but if you need help, we're in the Q&A chat. You have 45 seconds to go ahead and work on number 6 on your own, go, 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 and raise your hands. Do your best on number 6. This is a complete on your own.
So go ahead and tell us really quick with the little colored pointers. Let us know how you feel about today's lesson. All right, we got one pretty good. Couple still need some help. All right, that's what office hours are for. All right, we got a couple awesomes. All right, good to see that we're on the upper end of the spectrum there. So let's pause that for a second and just say that if you haven't already, go ahead and submit your notes. Tell us how you did. And if any of you still need help or need to go back and view a previous question, feel free to stick around for a couple minutes. For those, the rest of you who are ready to leave, go ahead, have a great day, and we will see you guys tomorrow.